work together a lot. So most of the work here is stuff that he's contributed some things to, and I've contributed some things to as well. So without further ado, start with the kind of simple, what is a compression driver? So it's a driver that's specifically intended to attach onto a horn. And the idea is to try and make something that's extremely efficient. And a horn helps to increase the radiation resistance, meaning that you can get more efficiency. But a compression driver can get even further because it allows you to use a large diaphragm. So, for example, this diaphragm of size D2, but couple it to a small horn throat. And when you do that, you get an even higher radiation resistance. There's another key point, which is that normally with a radiator, the size of the diaphragm is pretty critical for its directivity, and especially in a direct radiating loudspeaker. That's one of the major considerations for different sizes of driver. But this arrangement breaks that rule, really, because it's more the horn throat that determines the directivity in a situation like this. But really the key point is that it only really works when everything's behaving very well. And there's quite a lot that can go wrong. So what we're relying on is that this chamber of air that sits in front of the diaphragm just behaves like a compliance, and ideally a very small compliance. Because if that's vanishingly small, then whatever volume velocity is created by the diaphragm is going to be replicated in the horn throat. So really everything that we're doing when we're designing a compression driver is to try and maintain that ideal. They've been around an awfully long time. So this is the kind of classic, it's not the first, but it's regarded as the first really well-designed compression driver, the Western Electric 555 from 1929. So only a few years after Celestion were founded. These guys went and through us. They have, if you're interested, have a look on like Google patents, look them up. They've got all sorts of inventions on acoustic devices. They came up really with the first serious compression driver, this one, and it had things like phase plugs, and really got it working quite well. So it can work over quite a wide range. If you put it on the right horn, about 100 Hertz up to 5,000 Hertz. And you can get an overall efficiency of around about 25%, which is very important in 1929 because you don't have powerful amps. The other thing that's interesting about it is it doesn't have a permanent magnet. So it would use a field coil, so a second coil of wire that you put a DC current through to get magnetic field in the gap where the voice coil is. And when in 1929 these were used, they'd be put on very big horns. This is a system I heard a few years ago at a Munich hi-fi show. So it's actually two separate systems, so you don't play all four at once, but it was a stereo system. Each of these had a 555 driving them. And it was just being driven off a 2-watt valve amp, and it filled the room. And in some ways it gave it like really beautiful sound, but in other ways obviously very coloured as well. But if you were trying to have kind of a big audience of people, whether that was some kind of gathering for announcements or say a public movie show or something like that, you'd need a system like this to deliver the audio to them back in the 30s and the 40s. So a modern compression driver, in a way it's not very different, but we'll go through the parts looking at a more modern one. These days most use dome diaphragms. So this is a cross-section through a kind of a typical design, and you can see the diaphragm here, it's this dome. And there's a very, very, very thin compression cavity gap between the dome and the phase plug. So the phase plug is the structure that actually leads the sound from the dome through to the horn throat. So from the dome here through to the horn of the throat. And typically in a modern one you'd have several paths coming from the compression cavity to the horn throat. And we're going to talk more about that later. They have incredibly tight clearances. I mean, even though I'm involved in the industry and we handle these things every day, it always surprises me how tight the clearances are. So, for example, it's not uncommon for there to just be 0.5 millimeter between the diaphragm and the phase plug on something with maybe a 3-inch dome. It's quite hard to manufacture something like that if you're making, say, several hundred a week. So there's not actually that many companies who manufacture them, and maybe that's a consequence, that you have to be pretty sure you want to do it and pretty confident you can do it. Looking at some real parts, this kind of refers back to the previous picture quite nicely. So here's a diaphragm dome. So very similar to what you might see on the front of a hi-fi speaker, except it's big. This is a 3-inch one, so 3-inch across. And it's also quite deep, deeper than you might see, which is an attempt to make it as rigid as possible. That then goes into the assembly like this, and this black cover is just covering up the back, and the sound is radiated from the concave side. And you'd screw it onto a horn like that. So there's your horn with it screwed on. So a lot of the reason for the work that I started doing on compression drivers, and the reason Mark was pushing it as well, was to try and make things that could cover wider bandwidths. So there's a few reasons why we were interested in that. I mean, Celestion don't actually make product that customers, consumers can go and buy. We sell drivers that other people build into speakers that people buy. So really we're trying to meet demands that we hear from them of saying, you know, this, if you had something like this, we could make, you know, whatever it is. So there's a few reasons that we've heard. So, you know, if we have a larger diaphragm and, you know, we still have to keep a very tight clearance to the phase plug, we can effectively get more volume displacement or volume velocity. So we can get a greater max SPL, or you could use the thing over a wider bandwidth and use that greater volume displacement to deliver more at the low end, where the diaphragm needs to move more. Or if we can get a bigger diaphragm, depending on how it's constructed, it might have a bigger voice coil and we can get more power handling. And these are all critical things for our customers, who are people who are going to build this into speakers, like this one, say. So they're after things that are louder, maybe more compact, but deliver the same performance as something big. Or they, say, perform better, but this is in the sense of they give better fidelity. So maybe they can use one horn that's going to produce everything in the mid and the high, where previously they were using 2 and getting some interference or some irregularity in directivity. So that was our goal, really, to try and increase the bandwidth. And you really straight away come across, you know, there being really big challenges in doing this, which we kind of always split into these 3 different sections, but they do all interact to an extent, and more on that later. So the first problem you have is that you've got multiple paths where the sound can come into the throat, and this whole structure is quite big, so it's very easy to get resonances in this structure. It's normally more than a wavelength, maybe more than 2 wavelengths, depending on how far you're trying to push it. The compression cavity itself, so this thin sliver of air, this of course has got its own cavity resonances as well, and they will be in the bandwidth as well, so you have to try and avoid them. And finally, the diaphragm is big, much bigger than you'd use, say, in a high quality studio monitor or hi-fi system. So just to give you an idea of that, if you had a 1-inch titanium or aluminium dome, if you do things very carefully, you might be able to get it to have its first breakup mode somewhere around 30 kilohertz. With a 3-inch, which is not uncommon, you're probably down around 6K, something like that. But people building PA systems are trying to use these to deliver high frequencies. So it's really pushing against the physics of what you can do with a diaphragm that big. So really, all 3 of these problems come down to the same thing. It's a big structure compared to the wavelength we're trying to produce. So what we've found in the industry, I should say, yeah, sorry, I mean, you can take lots and lots of these from the market, you can measure them all, and if you work out the upper limit of where they're working nicely, you'd normally find it's around Ka 5, so normalized wave number of about 5, just to give you an idea of where the state of the art. And some are better than others, some are worse than others, but that's roughly where it is. So what we've seen quite a few manufacturers do is try and combine two compression drivers into one, which is quite a neat idea. So this is a one device. Connect it onto the horn here. But actually, if you look in detail at it, you've got one 3.5-inch diaphragm here, and then another smaller 1.75-inch diameter there. So the idea is that you can use this one to generate more volume displacement for low frequencies, and then you could use this one at high frequencies because this one will probably be resonating out of control by that point. And these are really popular. Yes, sorry, they are both annular. Yeah, I mean, conventional compression drivers with one diaphragm tend to be domed still, but there are certain manufacturers that are starting to use annular diaphragms like JBL or BMC, and there's not that many people making dual diaphragm compression drivers, and the ones that I've seen are all annular, which is quite interesting. These are very popular. So people building PA systems like this, they stick it on one horn, they can get consistent directivity, cover a wide bandwidth. Now, we initially thought at Celestion, well, why don't we do that? We can come up with something, an arrangement where we have two diaphragms in one. So Mark and I started to think about that in a bit more detail, and we did some very simple numerical models to try and understand the challenges of that. And this was a kind of picture of the mesh of one of them. What we found is extremely useful when we're starting to plan products or find which path to go down is actually to use FE as a bit of a tool to do an abstract experiment. Because you can do things in FE that are very clean, where you can isolate just the things you're interested in and try and look at fundamental problems. So this gives you an example of that approach. So this is a tube. There's a rotation of symmetry down here, so I'm just plotting half of it. And we have two diaphragms connected to the left-hand side. We've got the blue circular disc and a little red annular disc. Because this is FE, not the real world, we can just say these are perfectly rigid, and they will be magically perfectly rigid. And what we can do here is we can move these and then see what happens in the plane wave tube. And this is a typical way you might measure a compression driver, connect it up to a tube and see what pressure you're getting in it. And theoretically, you'd want something that gives you even pressure at all frequencies. That would be the ideal. You can also see that there's two kind of short paths that they're separated into two paths here before they're joined up around here somewhere. So kind of to illustrate the problem, we solved these in the time domain. So we moved the diaphragms with a Gaussian step. That's shown in red. And that's because the pressure in a plane wave tube is proportional to the velocity of the diaphragm. So this displacement looks like that, but then the velocity ends up being the differential, which is this nice pulse that we should be able to see quite clearly. So look at some results. So the first case is what happens if we send the same signal to both diaphragms. So there's our pulse. Separate sections join up very nicely. That's great. We've got a little pulse traveling perfectly down our plane wave tube. But of course, that's not what we're going to be really doing in the real device. We're going to be sending different signals to the two diaphragms. So if we just drive the outer diaphragm, now you can start to see the problems. So at the point where the two join up, of course, this wave diffracts back down along and bounces back off the other diaphragm, and you get all sorts of mess behind your initial impulse. I'll let it play again so you can see second time round. So we also can do the other configuration and just drive the inner diaphragm, and I think you probably guessed the result. And of course, there's no way that the sound coming out of one of these little ducts knows it's not meant to go down the other duct. It doesn't know it. So this kind of nice idea of I'll put these two diaphragms in tubes and then join them up, and we'll just get a wave that adds up, isn't going to happen. So, you know, you might say, well, actually, you're going to use them both at the same time. Well, I've got that one as well. So this is if you have a crossover, and I've assumed the outside one's going to be high frequencies, the inside one's going to be low frequencies, and it's just a Linkwitz-Riley crossover. So, you know, having looked at this and thought about it a bit, we decided, well, do we really want to try and make one of these? How is this ever going to work? We had some ideas, you know, maybe minimizing the distances. But we thought it would be more interesting to say, well, can we do the same thing? So just, you know, recapping, these are the kind of 3 challenges of the wide bandwidth design. And actually, the dual diaphragm compression driver is doing quite well at avoiding resonance in the compression cavity and controlling the vibration, because we've got smaller diaphragms. It's not doing very well at avoiding resonance in the phase plug, in the channels between the diaphragm and the throat. So that became the challenge. You know, well, if we don't want to use 2 diaphragms, we're going to have to just do the same bandwidth with one large one. So, you know, as we saw it, we can avoid these phase plug resonances if we do that. But there's also other benefits for manufacturing potentially. So it is simpler, the assembly can be simpler. We don't have to have 2 motors, one for each voice coil. Maybe that leads to lower cost, although I don't know if that was true in the end, so we'll see. So we really went through the process of considering each of these different aspects of the phase plug in turn to try and understand the physics of it and then try and find solutions to it. And that's what we're going to do in this case. So we're going to run through that. So the first one we picked out was the phase plug. So the phase plug is really just a few channels that go from the diaphragm, which is over here, I haven't drawn it, through to the throat of the horn. And you can do some very, very simple models that you can learn a lot from them. So all we did was do duct models, in fact. So it's like I guess you might call them 2-port models. So each of these ducts can carry 2 plane waves, one traveling to the right, one traveling to the left. Except for this duct here, that we only allow a plane wave traveling to the right. So it's like an infinite tube. And this would be connected onto a horn, but that's quite a nice approximation, just an infinite tube, just for the time being. And if you analyze this, you can just write out, you know, the equation of what the pressure is compared to these velocities, or what the impedance is at each of these entrances. And it tells you, you know, how is the throat pressure affected by the velocity, the acoustic velocity at each of the channel entrances? How is it affected when you change the length or the area of the different channels? And what's the acoustic impedance at the channel entrance? And so that's quite a lot of information that you can learn very quickly and try and, you know, come up with some design guidelines. So yeah, you can do this yourself, but I've saved you the time. So it looks horrible, this expression. So this is, you know, really relating the 3 volume velocities, Q1, Q2, and Q3, at the beginnings of each channel to the throat pressure. And it's pretty horrible. And you can see, you know, lots of sines and coses, and of course those all go to 0 periodically, which means that this pressure could go infinite at a number of places. But it's kind of quite easy. If you look at this for a few minutes, you can see, well, actually, if I make up some rules, if I say L1, L2, and L3, so the length of these 3 is the same, and the area of these 3 adds up to the area of the throat, then this horrible thing just becomes this thing. So the pressure at the throat is really just a combination of volume velocity rather, at the entrance to each of the 3 channels. It's very clear. So we have straight away a design rule that we have to meet. So the second thing that we can learn from this kind of a very simple analysis is, well, what kind of impedance would we see at the beginning of each channel? So I've already assumed we've met that criteria of the same lengths and the areas adding up to the throat. And again, you get something like this. But again, if we make some simple assumptions, so in this case we say, well, the acoustic velocity entering each channel is the same, then really what we see is that we just get the throat impedance. these channel entrances, which is all very, very tidy. So that's, I don't think, a surprise to many people. It kind of makes sense that, you know, if you take a tube and you split it into 3 small tubes, as long as you keep them consistent areas and consistent lengths, everything's happy and it's all going to work. That's also kind of what we saw in that FE model where we drove both of those separate diaphragms with the same signal. It all just summed up. So it's a good result though, because it very succinctly tells us what we need to do when we're designing these. So equal path length, combined channel area is equal to throat area, and we need identical velocities at the start of each channel. And if we do that, then we also know that the specific acoustic impedance at the start of each channel is going to be about rho C. Well, actually, it's going to be approximately the impedance of the horn you put on it, specific acoustic impedance of the horn you put on it. So that was nice and succinct. So now we move on to the second challenge. So we already know some stuff from our previous analysis here. So we know, for example, that we want the same velocity at each of our channels. Sorry, the same acoustic velocity entering each of our channels. And we also know that if we do that, then the specific acoustic impedance of each channel is rho C. So therefore, it's very obvious that you need the same pressure at the beginning of each channel in order to achieve that. Thanks, Bruno. So that's all very well, but we already know as well that this cavity is quite big and it's likely to have resonance. And we will get modes within the bandwidth we're trying to use. So what we have to do is treat this like a modal cavity. And actually, it turns out somebody's already thought about this problem. As you find quite often in acoustics, somebody's already thought about it. And in this case, it's a chap called Smith. And he thought about it in, I forgot the date on the next slide, but I think it's 1950. He's already well ahead of us. But what he realized was that if you've got a perfectly flat diaphragm like this one, then that's driving the cavity totally evenly over its whole surface. So it won't excite any modes itself. It'll only create static pressure. It'll only excite the breathing mode of the cavity. So the only way that you can get modes excited here is because of the volume velocity leaving the cavity into the channels. And he realized that if you very carefully position the channels, you can balance the excitation of the modes from each of them to cancel. So I've got an FE model to demonstrate that. So here's one that doesn't work. So I'll explain the model. So axis of rotational symmetry here. On the very left of the cavity is a diaphragm, which is just a disc, and it's perfectly rigid. And it moves with constant harmonic velocity, unit harmonic velocity. And in this case, we've got 3 channels, but we could have as many channels as we like. And each of these channels is terminated with a rho C impedance, which means they're infinite. They keep going on forever. And if you just plonk down your 3 channels in any location and make them any size, when you look at the pressure at their entrances, this is the kind of thing you get. So it's all fine until Ka of around about 4, and then it goes pretty horribly wrong because of these modes in the cavity. If you follow the Smith guidelines, so he describes how to derive the positions of the channels and the widths of the channels, then you get almost a perfect result. Incredibly good, in fact. And of course, he was doing it all, I guess, on the back of napkins. Whereas we can test it now with FE models. So how's that working? Well, as I said, the diaphragm itself isn't exciting the higher order modes of the cavity. The only thing that's going to be exciting them is the acoustic velocity entering each channel. And in this case, we've got 3 channels, which means we can only really control 2 modes. And what you see is, what I've drawn here is for each of them, how much each channel is exciting each mode. So mode 1 is not really excited by this channel at all, because it's quite close to the node of the mode shape. But it's excited quite heavily by the outer and inner channel, but in opposite directions, in opposite polarities. And you can see how Smith's method works, that if you visually add up these three lines, it cancels, comes to 0. And the same for the second mode. In the case of the second mode, this one's exciting it quite severely, and the outer and inner less so, but they're in opposite polarities, so you can control it. So it's very elegant, and something that the industry is quite well aware of. If you look at most compression drivers that are kind of simple one diaphragm compression drivers, if you open them up and you measure where the channels are and how big they are, they're following these rules. So it's quite well established. Maybe people are just copying other things as well, I don't know. Sometimes it's hard to tell, but it's the way it's done. Of course, it's not perfect, and Mark and I did quite a lot of refinements to it, because this idea that the diaphragm's only going to excite that breathing mode is only true when the diaphragm's perfectly flat. As soon as it's not flat, so if it's a dome, it will excite. But of course, you can use a similar approach. You say, well, now I've got 3 channels and a diaphragm exciting each mode. So all I have to do is make sure that all balances for the first mode, all balances for the second mode, and however many you want to do. So we did quite a few different refinements of this idea. First of all, saying, well, most compression drivers are a dome, so let's tackle that one. Then saying, well, you might not want a dome, you might want a cone, so let's tackle that one. And then finally, we were bothered by this little spread we always got, but we figured out what was going on there for this one. And this is actually slightly better because of shading of the cavity, which we talk about in a minute. Great. We can all go home. These all assume the dome's rigid, and it really isn't rigid. It's pretty horrendous. So that's 12 kilohertz on our kind of typical 3-inch diaphragm. It's not rigid at all. And that's something that hasn't been considered a lot in the theory of how to design a compression driver, because it's a bit of a pain. It's much easier to do your analysis with a rigid diaphragm. You get these neat results. But eventually we decided we're going to have to try and figure out what's going on. So I'm just going to flip back a second, just to say, well, this geometry here, I'm going to use it again in a second. So you can see with this geometry here, with a rigid cone and dome, we were getting really perfect results. So just repeated the same geometry and said, well, what happens if I actually put some realistic parts on this? How much worse does it get? So I reran the model. It's got a titanium cone and dome, a little voice coil on it, and a little titanium former. So we go from something where when it was rigid it's behaving like a textbook result to something where it's actually pretty horrendous, and you might not have, maybe you shouldn't have bothered doing all those calculations for where the channels should be. It's so bad. What was the point? So the first thing we did was to try and say, well, can we put this in some context? We've got this diaphragm which isn't rigid, but we really want to quantify its irrigidity, if that's a word, in terms of what we're looking at, which is the excitation of the cavity. And in the papers we'd written the extended Smith's method, we had this consistent term here, which you just end up with amplitudes, but this is an integral over the velocity of the diaphragm, so the normal velocity of the diaphragm multiplied by the mode shape. That really just tells you how much each cavity mode is going to be excited. So we have these diaphragm excitation factors. So cavity mode shape times the normal velocity and integrate it. And when you do the modal suppression calculation, so the calculation that tells you where and how large the channels should be, you're using these normalized factors. So how much is mode 1 being driven by the diaphragm compared to mode 0? How much is mode 2 compared to mode 0? And what we'd already shown is the optimal case is really when the diaphragm's only driving that breathing mode. And that's a kind of formalization of Smith's findings too. So the first idea that we had was, okay, well, it's very simple. Now, we haven't got a constant diaphragm velocity, but it's frequency dependent. So that was how we started to think about putting a framework around this. And what happens is when that becomes frequency dependent, the integral becomes frequency dependent, and these factors become frequency dependent. So we kind of slightly changed terminology. They were factors before, now they're functions. But if you just ran through the normal calculation, you'd end up needing different channel sizes for different frequencies. So that doesn't really help us at all. But one thing you can do straight away is look at them. And that turned out to be quite useful. So, we're now looking at these excitation functions. So how much is the diaphragm exciting mode 1 in the cavity, mode 2 in the cavity, and mode 3 in the cavity? And then if you look at the pressures we were getting, it was working down here and it's not working up here, and you can see why. At the point where it's approaching 0 dB, so at the point where the excitation of the other mode is approaching the 0th mode in the cavity, it goes wrong. And it also kind of makes something else quite clear, is actually it doesn't really matter what these are if they're small enough. Provided we're exciting the breathing mode of the cavity substantially more than every other mode, then we should get a good result. So that then feels like something more tractable. So we don't have to make our diaphragm rigid anymore. We just have to make sure it doesn't drive the higher order cavity modes. Does that make sense? Yes, good. I thought it did. So you then have to say, well, how am I going to design a diaphragm that does that? It's allowed to break up, but it's not allowed to couple to higher order modes. And you need to then look a little bit deeper. So you need to then say, well, probably the diaphragm is a modal system as well. So we took the diaphragm of the velocity and said, well, let's describe that in terms of its mechanical modes. So the mechanical modes are here, the large theta. And we can actually describe the excitation function. So how much is the diaphragm exciting each acoustic mode as a summation over each mechanical mode. And really there's just two key terms here. So this one, again, it's an integral over two modes, but one's acoustical and one's mechanical. So it just describes how effectively each mechanical mode couples to each acoustical mode. And then secondly, how much are we driving each mechanical mode? So we end up just with two things: a modal coupling factor, the coupling between the acoustical and the mechanical parts, and a forcing factor, how much are we forcing the mechanical modes. The asterisk is to remind me to say that could be a force because you've intentionally pushed it with a voice coil, but it could be a loading as well. So it could be that the pressure in the cavity behind or the cavity in front of the diaphragm is loading the diaphragm. So it adds a little complication to it. So there we have quite a key result. So we're trying to minimize the excitation of other modes in the cavity, and we're saying we can do that if we minimize the coupling between the acoustical and the mechanical modes. So that leads to quite an interesting thing. You say, well, no, really, this expression here was this integral of two different modes multiplied by each other, and I only want a result for the particular diaphragm mode that I'm using to generate sound. So you can kind of say, well, that's, just, you could times it by two delta functions here. And that looks, if you're familiar with modes and orthogonality of the modes, that looks like an expression of orthogonality. So there's other expressions of orthogonality in the system already. So we have orthogonality over the acoustic system, which says if you take two modes and you integrate them over the volume, it'll be zero unless those are the same modes, unless those two modes were the same. And the same on the mechanical side. If you integrate two mode shapes multiplied by each other, it's only non-zero when they're the same. And this kind of additional expression says, well, this is really like a condition for bi-orthogonality. Two families of functions which are in themselves orthogonal, but when you combine them, they're orthogonal as well. So then that was the next bit to say, well, maybe that's what we're looking for. An ideal compression driver is one where the acoustical and the mechanical modes are orthogonal. So we kind of thought, well, this is now an impossible thing. We've got to find something which behaves like a set of functions. Is that really going to be achievable? So the main example of two orthogonal families of functions you'll be familiar with are sine and cosine. So if you take these and you integrate over a cycle with a cosine times a cosine of a different frequency, a multiple of the frequency, it goes to 0. Or if you do cos times sine, it goes to 0, unless they're the same period, unless m's the same. So realizing that that's the prototypical example is quite reassuring in a way, because you can look at those and you think, well, now it feels quite achievable. If I can get something where the mechanical modes look like sine and the acoustical modes look like cos, I'm in with a shout. So if you think about a cavity mode, it's going to have a pressure maxima at the walls. So it's going to look a lot like a cosine. It's going to be, a bit wonky maybe, but it's going to have a pressure maxima at the walls. So then that kind of almost dictates that we're looking for something which has got, on the mechanical side, a velocity minima at the inside and outside edge. But again, that's okay, we can do that. It just means we have to clamp the diaphragm at the inside and outside edge, so it forces these velocity. And then it might be able to get modes that look a little bit like sine waves. So along with this, we came up with the idea that we could compute these coupling factors very quickly now, because it's just from modal results. FE modal analysis is extremely quick, much quicker than doing a sinusoidal analysis. So what we decided is we'd plot them out like this. So up the vertical axis here, we'd plot acoustical modes along the horizontal mechanical modes, and we'd do a level version of our mechanical to acoustical coupling factors. So for the example we looked at earlier that suddenly didn't work when it was not rigid, that's the kind of thing you get. It's still quite hard to see what's going on there, so we came up with a slight hybrid of that, which was we also account for where we're driving it. Where's the voice coil? So we add in a forcing factor. So again, that's not a complete forcing factor because it doesn't account for loading. But what you can see is now it's kind of highlighting that this coupling here is the problem with that particular design. And I haven't got it easily available. If you flicked back to the one that looked at the pressure result, you can see it's really exactly here where you're getting the biggest problem. So from that we outlined, well, let's build a cost function based on this map and then try and minimize it. And it leads you to quite a neat little iteration you can go through. So you basically come up with a diaphragm, you do a modal analysis of it, you then generate a compression cavity from your diaphragm that needs to be perfectly matched to the geometry of it. From the two sets of results you can calculate the coupling factors and the forcing factors, and then from that you can have a cost function that you're going to try and minimize. And it's quite quick, so even for a 3D model you can run through one of those in, if you do it well, you can do it in about 5 or 6 seconds. But if you're doing a full sinusoidal analysis to predict pressures, it's going to take probably a couple of hours and you'd have not a lot of chance of doing many iterations. So one thing I kind of skipped over here is generating a compression cavity. There's a trick you can play. So we already know what we're aiming for, which is that the mechanical modes don't couple to the acoustical modes, except for the one that we're trying to get volume displacement from. And we already know as well that all of the acoustical modes are orthogonal to each other and all the mechanical modes are orthogonal to each other. So that means if we make the 0 Hertz acoustical mode look very, very like the mode that we're trying to get volume displacement from, we already solved the problem for k equals 1. So what that means in simple language is you make the thickness of the compression cavity proportional to the volume displacement you're going to get from the diaphragm. So it's very simple, it's just shading it. So where the diaphragm's clamped, it comes down to 0. Where it's moving a lot, it's a thick cavity. And when you do that, you already meet your target for k equals 0. So only the first diaphragm mode is going to give you the 0 Hertz breathing mode. So that means in our iteration process, we can just knock out the geometry for the cavity automatically without any other calculations. So this was the test case that I put together in my thesis, actually. So it's kind of I guess biconic kind of diaphragm. It's got a cone on the outside and a cone on the inside. But then, of course, I knew that it had to be clamped as well. So it kind of has a bit of a surround on the inside and the outside that's going to flex, and it's clamped so it can't move. And I put in some fairly sensible materials. It's not really a practical thing. I think if you built it, it probably wouldn't work very well. But it's just a test case. So using this, we ran through the process and we calculated the coupling factors for 14,175 different variations of the geometry in 4 hours, which is really quite good. That was the final result, at least the one with the lowest objective function as I'd defined the objective function. On the end of that, we then need to design a phase plug, so put 3 channels of areas that meet a kind of Smith-like criteria. And this was the result that you get out at each of those. So this is the pressure in each of those 3 channels when they're infinitely terminated. So that's actually was quite an encouraging result for us. This is 12 kilohertz contours plotted there, and you can see just visually 3 plane waves that look around the right phases and amplitudes disappearing off. And in the plotted results, you can see the effects of the diaphragm modes, but they're not like they were on the unoptimized one, where you're getting big variations between them. They're much smaller. So that was the point where I finished my PhD, and we kind of at that point we knew that actually we kind of slightly shifted our perspective on compression drivers. Previously we were always aiming for the most rigid diaphragm we could possibly get. And this made us think, actually, if we've got a diaphragm with the right modes, it doesn't matter if it isn't rigid. We showed a bandwidth improvement here. So, if we say, well, this kind of level of irregularity is probably acceptable, then we're actually pushing things up towards a Ka of 10. And it's also quite nicely complementary to the historical methods. Everything we've done fits into really the same framework. It's building on it. So then the challenge was, well, let's try and make something commercial that we can produce based on this. So the second section is, as I said at the beginning, it's kind of a combination of my work and Mark's work, but the second section is something that certainly Mark had a lot to do with, actually trying to figure out what a diaphragm looks like that does this. So before we jumped into it, we kind of started examining what a diaphragm shape, an appropriate diaphragm shape would be. And it's worth just comparing kind of conventional approach to what we're talking about here. So conventionally, you're aiming for something that's rigid. Resonances cause regularity. You can't really use a diaphragm when it's resonating badly, but sometimes people use it to get a little bit of extra HF. So when you're designing the diaphragm, you're really trying to push up the first resonance as high as possible. And normally they're supported by some flexible suspension. So you have a very rigid diaphragm and then some surround that is designed to flex. So what we're saying is quite different now. We're saying we want to control the mode shapes. We know, because it's got to be like this bi-orthogonal series, that it's probably going to have to be clamped at the inside and outside, so that we get velocity minima there. And that means that volume velocity to create sound output really has to come from the diaphragm flexing. It doesn't matter so much that the first mode is high. It's probably more important that we don't have too many to think about. If we have a diaphragm that's only got, say, 3 resonances, it's going to be easier to control everything than if it's got 10. And it's okay to have a few of those in the working range. So normally people would use a dome, like this. And with a dome, one of the interesting things, if you've never done it, is if you change the thickness of a dome, its first resonance, its axisymmetric resonance, doesn't really change frequency. That's because you remove stiffness at pretty much the same rate you remove mass, because the stiffness is all coming from hoops of material, so membrane stiffness. And if you just cut a slice out of a dome and analyze it in the same way on its own, you'll find the first mode becomes like 100th of the frequency of the full thing. So it's deriving all of its strength from hoop stiffness. The other type of diaphragm you quite often see in compression drivers are these kind of biconics, so an annular diaphragm with a kind of cone on both sides. But this also relies on hoop stiffness. So stiffness in being carried around a hoop of material. It's quite interesting to compare them though. So we made some FE models of two diaphragms with the same radiating area and the same voice coil diameter, just to have a look at where the modes were. And you see quite an interesting pattern. So the dome has, to explain this plot, this is just mode number versus frequency. So you can kind of look at where the modes lie. So the first mode of the dome is higher, but then the third, the fourth, the fifth, they come in very, very, very rapid succession. So if you were trying to do this by orthogonal series up to 20K, I don't even know how many modes you're going to have to consider. It's probably 40, 50 maybe. And that didn't seem practical for us. We were kind of aware that anything you do to this mechanical system is probably going to shift the modes, and how well can we model them and how well can we build the thing. The biconic's quite interesting because it doesn't do as well for the first mode, but then they're more evenly spaced. So that you only have to go up to kind of about 15 before it's above 20 kilohertz. And that made us think, well, maybe this is a nice way to assess the dome. We really want something where this line is quite shallow, so we've only got a few modes to worry about. We also knew we wanted a very big diaphragm, so we started to look at what happens when you scale diaphragms. And the thing about a diaphragm that derives from hoop stiffness is that it gets very weak when you make it big. It gets weak very quickly because the hoop of material providing your stiffness has got a lot longer. So if you double the diaphragm size, you get about half the resonance. This was an interesting one. If you take the biconic diaphragm, you've got another option for making the area bigger, which is just to increase the width. So effectively you make the OD bigger and you make the ID smaller. And that's interesting because you can get more area without as much penalty. But ultimately, these are all kind of clues of the final direction, and we decided to do something a bit different. We decided to make an axiperiodic diaphragm. So an axiperiodic, you've got something where it's not symmetrical around the center, but it's got repeated features. This particular one's what we call reflective. So these are kind of planes of reflection. So only one of these segments really defines the whole geometry. And the neat thing about a geometry like this is that because of the symmetry, you kind of know that nothing can move off any of these planes. So you're almost like adding stiffness by having features that repeat. The really interesting thing about this became obvious to us when we started modeling it. So here's a kind of very early thing. So as I said, if you just have one segment of this, it actually defines the whole thing. So when we model it as well, it's quite efficient. So here's an axis of symmetry. The yellow here is where we would glue the voice coil, so that's perfectly planar, a planar circle. And then we've got something which is kind of bulging out and then coming down the other side, so it kind of waves as it goes around. So when we solve that, it looks quite a lot like the biconic in terms of its proportion of layout of the modes. So the first one's happening around about 7 kilohertz, which is pretty similar to the biconic. And we end up only having around about 11 up to 20 kilohertz. But if you double the size of it and you double the number of features, what we found is the modes didn't change really. Very, very small penalty for them. Because most of the stiffness is derived from the complexity of your repeating shape. So as long as that repeating shape doesn't change in size, there's not much penalty for making it bigger. So that's the type of diaphragm we settled on using, with something with this very rapid, repeated features around as you go around the circumference. This was actually the final FE model. So I've jumped ahead a bit because there are a lot of iterations to get this to this stage. It's quite an interesting shape. There's a full picture in a minute. Again, because it's fully defined by a segment, we only need to model a segment, which is a big advantage because you can run the analysis very quickly. It's equivalent to a very, very big dome. It's, I think, equivalent to around about a 4-inch dome diaphragm, so it can move a lot of air. When we analyze this as well, we're checking the stiffness versus displacement in the mode that we're going to generate the volume displacement for to make sure it's nice and linear. And it can move out to 1 millimeter in either direction in quite a linear way. It took us thousands of models really to get to this shape, and lots of attempts that didn't go right. The final coupling map looks like that. So again, just to recap, these are all the acoustical modes. These are all the mechanical modes. The ones inside the red box are the ones that we were forming our objective function with. So we were trying to force those all down and only have this coupling here between the flexural mode at 300 Hertz and the breathing mode of the cavity. That's the one that's going to generate our sound. To finalize the design, we added all the detail and ran it sinusoidally. So we designed a 3-channel phase plug. Again, quite interesting here. You can see normally these end up being very similar thicknesses, but in the case of this diaphragm, you get a much bigger thickness on the middle one there. And that's just related to how the volume velocity is created on the input side. That's the 3 pressures in our separate channels before we then join them up. So really going very, very smoothly up to around about 7 kilohertz, and then a bit of irregularity up to around about 15. So that's the Ka of 10. So conventionally we're down here somewhere, so we've been able to push it up an awful lot. Of course, you then have to put it onto a full driver. That's quite a challenge as well. We've got something that's very big, but it's got to have these channels pulled in so that it can fit onto a horn. If you remember right back at the beginning, we had a nice guideline for that. These channels need to be the same length, and the area of the channels needs to be consistent when we join it onto the throat. This is a FE model. This is a conical horn that goes off into infinity. Quite a nice test case. It's a bit better than a plane wave for a real world situation. And these are the pressure contours at 10 kilohertz, which for pro audio guys, that's pretty much high frequencies. That's as high as they can hear. But you can see, as much as you can ever see on these things, you can see the phase in each of the 3 channels is about even, and you can visually see the amplitude of each of those waves is about even. So it's working pretty nicely. We've made production tooling for this. Here's the critical thing I was trying to remember earlier. So it's roughly equivalent to a 5¼ inch dome in terms of how much air it can move. And you never get a 5¼ inch dome to work up this high. We also found we could make it from extremely thin foil. I think that's something to do with the stiffness of the structure being derived from all the features. So you wouldn't normally be able to go that thin on a big part like that because you couldn't handle it. It's got a 5-inch voice coil, which is very good for thermal power handling. That's what it looks like. So you can see the kind of repeated feature all the way around. It's got a clamp on the inside edge, a clamp on the outside edge. That's the voice coil. And the thing kind of flexes in order to create volume displacement. We're looking at the back of the diaphragm here. So, you can see just in the background there's the magnet system. This is the gap that the voice coil sits in. So this voice coil sits in that gap. The sound comes off the other side of the diaphragm through these 3 channels. that is the outside wall of the outermost channel. You can't see the other two in this picture. So it's a yeah, if you took a scalpel and you very carefully cut down there and down there, you'd get that. But the reason it's got so many repeated features is because it's big. That was the key result really for looking at the axiperiodic type diaphragms, is it's the feature size that's giving this its rigidity. So we can make it big as long as we keep that feature size small. It in a way, it's just a mechanical challenge then of trying to form that and assemble it consistently. We've got a 1 millimeter gap between the front of the diaphragm and the face plug at its widest point, but it actually comes down to almost nothing where it's clamped. So part of the challenge here has been mechanically to try and repeatedly produce this thing. So in terms of some results to look at, on the left here we've got one of the prototypes measured on a plane wave tube. So it's on a plane wave tube, which means it's incredibly loud. So just bear that in mind. So it says 140 dB. That is real because it's going into a tube. Of course, you wouldn't get that when you put it on a horn, but this is quite a nice way to assess and compare compression drivers. It's not so good at high frequencies. And as you saw when we do the designs, we design the compression driver assuming that we want a wave that's going to expand into a horn. So if you put it onto a plane wave tube, you tend to then excite some modes in the plane wave tube up here. But it's a good way to do comparisons. So on the right here, this is one of those dual diaphragm compression drivers, which is typically what customers are using, saying, well, can you make something big? So this is what we're up against really commercially. What you can see here is the sensitivity is pretty similar, but you hit the kind of breakup point of the big diaphragm around about here. And you can see in the impedance as well, this is the electrical impedance. That's where the crossover is. There's a little electronic crossover to hand over to the other driver, and it comes in about here and then again breaks up around here. So when you overlay these, in some areas we're losing out sensitivity-wise, but in others we're not, so kind of filling in bits where there's a bit of a gap between the drivers. And we're certainly avoiding kind of resonances low down on the diaphragm like this one. But really one of the key things that our customers have picked up on is this difference. This is the second harmonic. And if you look down here, there's a huge difference between the level of the second harmonic, because our diaphragm's got the ability to move a lot of air. This distortion is mostly coming from the mechanical limiting of the suspension on the diaphragm, and we don't have that. So just to put that on the same plot, if you look at how much SPL you can get out of it for 10% harmonic distortion, you can see a big difference here. So our design's going something like 15 dB louder down at the bottom end, which answers one of their requirements was a driver that you can use lower, so you can cover a really wide bandwidth. Interestingly, it doesn't. These are really, really identical. Well, that's because on a compression driver, you've got very, very high SPLs in the channels. So you get a lot of distortion because of nonlinear acoustics. And if you don't change the throat size between drivers, that's going to be pretty much the same. It just depends on how much SPL you've got through the channels and at the throat. So that's why it's more than a coincidence that it's identical. That's why it's identical. So that brings us to the end. So a few conclusions. So we ended up thinking that we didn't want to make a dual diaphragm. We could see the fundamental problems in it, and we set ourselves a challenge of doing it with one diaphragm. We've tried to outline a methodology really for how you can design these things. On top of that, this idea of using axiperiodic diaphragms is, I think, a fairly new thing in compression drivers. And we've got production parts for this now. It's not in any real-world products that you can go and hear or you can buy, but we have delivered them to some of our customers. And that takes typically quite a few years for things to actually end up on the market. But this kind of a big compression driver, I think one of the main application areas will be things like cinemas, where you wouldn't Some people might do it, but I don't think you'd put these into line arrays because they're too big, and it's quite useful to have multiple drivers so you can steer them in a line array. But where you want to have more or less a point source in multiple positions like a theatre is a typical use case. So yeah, that's it. So I should absolutely say thank you to everyone else involved. I mean, it's very much a collaboration. On the research side, particularly with Mark, he tends to suggest crazy ideas and then I try and put theory on them. But of course, the thing I haven't really spoken about is the mechanics of trying to make a big diaphragm fit in a structure where you've got very, very tight clearances, and there's been a lot of work on that by the Celestian engineering team. So, thank you very much.